Right then, question 3, and it's all about stars. So a star's continuous spectrum approximates to that of a black body. What is meant by a black body? So a black body is basically a perfect absorber of all frequencies, a perfect absorber and emitter of all frequencies of radiation. So there's only a single mark here. I think we can probably get away with something pretty brief. Perfect absorber of all incident radiation. That should do it. So Sirius, 8.1 times 10 to the 16 meters away. We're given an intensity here reaching Earth, 1.2 times 10 to the minus 7 watts per square meter. Sirius emits radiation equally in all directions. Show that the information leads to a value of this for the power output from Sirius. So this that we're given intensity-wise represents the radiation through a single square meter at that range. So if we multiply that up by the surface area of the sort of imaginary spherical shell of that radius that all of the radiation from Sirius would pass through, we will get our answer. So the power is equal to the intensity that we've got multiplied by that surface area that I mentioned, and the surface area of a spherical shell is 4 pi times the radius squared. So that's going to give me 1.2 times 10 to the minus 7 multiplied by 4 multiplied by 3.14 multiplied by, and this is going to be a largish number, 8.1 times 10 to the 16 squared. Let's commit that to the calculator and get a number. It's worth bearing in mind when you have a show that if the show that is approximate, especially if it says show that something is approximately, you do need to calculate the exact answer. Don't be tempted to just write down what the calculation is and then put a sort of approximately equals to the number given. Do calculate your own value for it and write down what that answer is. So just putting this in the calculator now. And I have 9.8887, so 9.89 times 10 to the 27, which is approximately equal to 9.9 times 10 to the 27 watts. Suggests my actual emitted power will in fact be more than that. So this, what will that be? This is the intensity of the electromagnetic radiation reaching the Earth. This distance in between is absolutely colossal. So you know the space, the vacuum in between stars is not perfect. It is a very thin gas, very, very thin, but when you're traveling at 0.1 times 10 to the 16 meters through it, you're bound to get some absorption. So we can just write something to that effect. Some absorption by interstellar gas will occur. I guess you could also have an answer in terms of scattering from interstellar dust or something like that. The surface temperature of Sirius is that, using Stephan's law, estimate the effective radius of Sirius. So from memory then, obviously you won't do it from memory, you'll check the formula book. But Stephan's law is something like this. Power output is sigma A T to the 4, and I'm after the radius. So A, the surface area, is 4 pi r squared. So putting that in, I've got P is equal to sigma 4 pi r squared T4. So R is equal to square root of P over 4 pi sigma T4. And this is going to look pretty messy, to be honest, but Plug in all those numbers. What have we got for the power? 9.9 times 10 to the 27. This would look slightly neater if I was writing on paper, I promise. Divided by 4 times 3.14 times Stefan's constant. Can I remember Stefan's constant? I think it's the 5678, isn't it? 5.67 times 10 to the minus 8. Let's hope it is. Multiplied by 9900 to the 4. Obviously, again, you guys would check the formula sheet rather than hoping for the best you've remembered it right. So that is a substantial calculation. Let's chuck that in the calculator. To be honest, calculations of this ilk that have a lot that can go wrong, I quite like to do twice, just on the grounds that it's easy to make a mistake. And in addition to it being easy to make a mistake, it's often very difficult actually to have an idea of what your final answer should be when you're dealing with things like stars, because the numbers can be so absolutely enormous that it's very hard to tell whether you're right. So first time round, I've got 1.2 times 10 to the 9 meters. Which is pretty enormous, and so I'm just going to plug that into 4 pi r squared t4 sigma to see if I get the power that I should get, just to satisfy myself that I have got the right answer. And I get 9.9 times 10 to the 27, so yeah, it looks like that's okay. Alright, part 4 then. The continuous spectrum of Sirius is below. Sketch the spectrum of the Sun. The Sun's temperature is that. That is less than the temperature of Sirius by a reasonable margin. Assume that the surface areas are approximately equal. So given that the temperature is substantially lower, once that's raised to the power 4, we're going to get substantially less power output from the Sun compared to Sirius. And the surface areas are pretty much equal. So power per unit wavelength, we're expecting a lower line here. We're expecting the Sun to not give out as much power per unit wavelength. In addition to that, this increase of wavelength the Sun's lower temperature means that there will be a substantially increased wavelength at the peak. So some line that is lower throughout will probably get us the marks. Right, is this the last part? Yeah, it looks like it. So dark lines are seen crossing the continuous spectrum. Explain how these lines arise. So these are Fraunhofer lines that we're talking about. They are absorption lines. So we just need to describe how those are formed. So basically what's going on is the particular elements in the atmosphere of the star will absorb specific frequencies that correlate to electron transitions within those atoms. So we just need to put that in words for 3 marks. So basically, atoms in the star's atmosphere will absorb specific frequencies of radiation where photon energies match electron transitions to higher energy states is how I'm going to phrase it. And I'm just going to read that back. 3 marks I'm looking for here. So what are my 3 marks likely to be awarded for? I'm guessing that I'm going to get a mark for saying there's absorption. I'm guessing that there's going to be a mark for saying it's specific frequencies. And I'm guessing that there's a mark for saying that those are caused by specific electron transitions. So hopefully I've done enough, and that is the end of question 3.